Here's Charles Amaggio. Welcome back to R for Epidemiology. Let's run through a quick example of using R for a linear regression model. We'll start off here by installing you should start off by installing the CAR package. CAR refers to Companion to Applied Regression. It is a package that was written by John Cox for to teach applied regression, and in fact this entire example is stolen whole cloth from Dr. Fox. In any event, if you have not installed the CAR package, do so. I'm not going to do that because I already have it installed. I'm just going to go directly to the library command to bring the CAR package into my workspace, which takes a moment. Once I've done that, I have access to a data set called the Duncan dataset, and we could take a look at a description of the Duncan dataset. It says here it is Duncan's occupational prestige data. Essentially, it's 4 variables. It's a type of occupation, the income of that population, of that occupation, education level, and a prestige index of some kind that was developed by the good people at NORC. This is from, I forget exactly when, 1950. So it is just purely for teaching purposes. We can, as we have all along, take a look at the data. It is a data set, just like any other data frame. And you could take a look at the head command. Take a look at that right there. You can look at the names of the Duncan data set. Well, they're right here, really. You see, for example, there's a type variable, income, education, prestige. If you want to make sure that you know the names precisely, you could use the names command. We see that there's, again, these 4 variables. You could use the structure command, get even a little bit more information to find out what kind of variable it is. We see that type is a factor variable, so that allows us to request a table of the type variable, and we see that there are, I forget exactly, we can go right back. Actually, you know what? We just go right back to the Duncan description and take a look at what type means. Type of occupation. There are levels professional, managerial, which is with white collar, WC, and blue collar. Alrighty. Things were simpler in the 1950s. So there are 21 blue collar professional professions, 18 professional professions, and 6 white collar professions. If you plan on doing a linear regression example, it makes sense to see whether something is actually linear. And we could use our QQ-normal function to do that. It gives us a little plot of the standard deviance arrayed by their sample values. It should be a straight line. If we need to be reminded of what a straight line is, we could use a QQ line to overlay a straight line on this. And these appear, at least to my eye, to be reasonably normally distributed. I think we could, I think we'll do okay with that. We can then do our first model. The go-to function for linear modeling is, easily enough, LM, stands for linear model. And the structure is you have a little tilde that we now know indicates a formula of some kind, and this formula is saying here that the Duncan prestige, basically we specify the name of the data frame and the name of the variable separated by a $sign. So prestige is a function of income and education, and that seems to make sense, no? Notice what we're doing here. We are saving it to a variable, to an object, to a name. We're naming this linear regression object because we know that when we name a when we save a linear regression, or we save any operation in R to an object, we can do things with that object, and the LM function creates objects of the class LM, and when submitted to generic functions, objects of the class LM return various and wonderful things. So we're going to run it, save it. Takes literally the blink of an eye for that to happen. So how do we get some of the results? Well, you could either just print it using the print command, or you get the same result just by writing the name of the object. So we did create this linear model object called Duncan model. Let's just return it, and we see this quite brief set of results here. It gives us the intercept, which is -6 on whatever scale they're using for prestige. And then there is the effective income, which is the rise over the run, or essentially for every 1 unit increase in income, there is a 0.5987 unit increase in prestige. Now, of course, when we're interpreting this, For example, what exactly does this intercept even mean? It basically means when this is the prestige when someone has no income and no education, and that's actually not really interpretable. And even income basically means this is the effective income when someone has no education. So these multiple linear regression models, and this is assuming that that income and education are measured on their natural scale. They're not normalized in any way or center meaned or something like that. But you need to keep this in mind. The interpretation is a little bit more involved than just simply that there is a 0.58987 increase in prestige for every 1 unit increase in income. In any event, back to R. This is a pretty brief summary, but in fact there is a little bit more information you can get by using the actual formal summary function. And the summary function, depending on what you submit to it, will return different things. If you submit a linear model object to summary, you receive this information here. You get the call repeated. Now you have the residuals, which of course you want to be centered around 0 and within reasonable bounds of some kind. You get the coefficients again, and these are the same coefficients we saw up here, but now arrayed as in a table, and with their standard errors and t-values and probabilities, a lot of stuff. Generally, you could just look at the estimate, take a look at the standard error, and double that standard error, and subtract it and add it, and see if it includes 0. If it doesn't, it tends to that indicates statistical significance. But to help you along, R gives you these statistical significance codes, a number of asterisks that help you. You get your residual standard error, and you can interpret it as you feel free, as you would like. I tend to think of the residual standard error as sort of like the average distance of the residual from the actual value. And residual is the difference between the fitted value and the actual value. The R square, which is it's interpreted, it's said it's the amount of information that a model explains. More formally, really, it is the residual variance. It's 1 minus the residual variance divided by the sample variance. So if the residual variance is very small, if it's a real good model, then the R squared tends to be larger. The F statistic, which you can just interpret as an overall test of the significance of the regression model. But anyway, this is how you sort of work with regression models. There are a number of specialty functions that are associated with regression models. There is a conf_int for the confidence interval that will return your confidence interval here. And there's a couple of other nice things you could do in regression. To illustrate them, it makes it easier. It's actually easier if we just have a simple linear regression. So I'm going to repeat the regression here, save it as the object Duncan model 2, and just regress prestige on income. Notice that I'm doing something a little bit different here, very little bit different. But here I used the $sign notation. Here I'm just naming the variables and then using data equal as an option to specify the data set. So here I'm doing a simple linear regression, prestige as a function of income. I run that, return it back. Now I have this model here. If one nice thing you could do is, for example, if you want to overlay a regression line on a scatter plot of 2 variables that you've included in a regression, here's one quick way to do it. First, you use the plot command and the 2 continuous variables that you want to do a scatter plot for to create a plot. And here is that plot. This is a plot of income and prestige. Then this very nice, neat little function, AB line, when given the results of, given a regression, a simple regression object as an argument, returns the regression line over the scatter plot, which is I find this really a nice feature. Whoever wrote this into R really was just trying to make things pretty easy for folks. You can also add a prediction. If, for example, you have a model, now I recall in this model that prestige, or that income stops at 80, or whatever that is, maybe $80,000. Well, let's say you want to not necessarily update this model, but you want to extend the model to include income values that were not in the original data. Now, this is always a dangerous thing to do, and I'm doing it here at the end. I'm adding values, and I probably shouldn't do it, but it's a nice way to illustrate some of the cool stuff that R could do. So I'm going to do it anyway. So I create a data frame that includes the new values that I want predictions for. And I name that data frame new income. I just go ahead and do that. And if I want to, I could take a look at this data frame. Here it is. It's a very simple data frame, right? New income is a data frame. And it is just these three values right here. Then I use the predict function, specifying my regression model, specifying the additional data frame, and then here's a little option. I want the confidence intervals for these new values here. So the predict function will return a very nice little prediction for the prestige based on these income levels here. So that's another nice little toy that you could play with in R. Plotting regression objects generally involves conducting diagnostic plots of some kind. So here is the QQ plot that we discussed, but it's a special version of the QQ plot. Notice that rather than the lowercase p, it's the uppercase p, and you may come across this, so it's worth looking at it. It's a nice version of the QQ plot in that it gives you these little simulations, and it also simulates the upper and lower confidence levels, and that's kind of a neat little feature of that. You can plot studentized residuals. Studentized residuals are just the residuals divided by the standard error, and by the residual standard error. And if you just request the studentized residuals, there is a function called studres, which is for studentized residuals. I'm sorry, these are the jackknife for studentized residuals. That's right. So in any event, I'm not sure if these are actually the jackknife residuals. I'll have to go back and check that out. For right now, I'm going to remove that until I have a chance to check it out. But right now, these are clearly the studentized residuals. Run those. Here are the studentized residuals themselves. Not a lot you could do with those. You can plot them. And here's a plot of the studentized residuals right here. And as you would expect, and as you want them to be, you want them to sort of like be around 0, but less than 2. Values between 2 and 3 values less than 2 are generally okay. Values between 2 and 3 are potentially of concern. Values beyond 3 are clearly of concern. You can see whether they are normally distributed with a histogram. And this is something that I did it here, actually. I'm doing it here as well. What I'm doing is I'm taking the studentized residuals and I'm taking the result, basically the results of a function, and feeding them to another function. So if I want a histogram of them, I can see that they're basically normally distributed. Dr. Fox has this nice little approach to playing with studentized residuals. So here, for example, you have the plot of the studentized residuals that we had, and he uses the AB line function to create lines 2 units above and below. Oh no, actually a little less than 2 units above and below. He uses a different cutoff. And this allows you to sort of like identify more easily outliers, potentially influential values. And one other tool that you could use to identify those influential values is, in fact, the identify function. And the identify function takes the index of the numbers of professions and the studentized residuals, and will return the names from the Duncan. And when you run this, what you do is you just run this, and then when you go over to the plot itself, you'll see that the plotting cursor turns to this little arrow here, and this little cross here. And when you click on a value, when you click on a one of the points here, you get the name of that point. So ministers are outliers here. They and that kind of makes sense. Perhaps they have high prestige but low income. A couple of other ones that don't really behave according to the model are contractors. Down here you have a reporter who maybe makes more money but maybe doesn't have a lot of prestige. I'm not entirely sure what that is. To stop this identify function, you right click. No points within 25 inches, and that basically does it. Okay, we're finished. The actual plot function for a linear regression model returns 4 plots, and what I'm doing here is I'm going to set up a 2x2 matrix to return those 4 plots. Once I ask for just the plot by itself, I get these 4 plots. And this here is a plot of the residuals versus the fitted values. You really want to see no pattern here at all. You'd like to see those residuals normally distributed. Here is the square root of the studentized residuals versus the fitted values. I believe it's interpreted the same. I don't use it. I believe it's interpreted the same as this, and I'm not quite sure what to make of the fact that there is no pattern here, but there is a pattern here that might indicate some sort of second order process occurring. I'm not quite sure what to do this. These here are the Cook's D statistics. It's a plot of the Cook's D statistics. There are a number of recommendations for cutoffs. The Cook's D or the distance statistic is basically the change in the parameter estimate after deleting an observation. And it looks to me that this one over here might be, this is whatever index number 16 is, and I'm wondering whether that was included in this. It didn't come back here, but in any event, these are the plots you'll get. You can update a regression object using the names of that regression object itself, and here's one way you could do it. First, you can get the actual. Let's say we decide that ministers and conductors are influential observations, and we want to update the model and look at the model without ministers and conductors. I wouldn't necessarily recommend doing this, but here's an example of how you can update a model anyway using the update function. And yeah, usually you'd like to explain this stuff rather than just get rid of it. But let's return. What we would do first is return those observations, return those professions, the index of those professions, and we use the which names function to do that, which is a neat little function. And we say, okay, which of these names are in the Duncan data set if you had to index them along by row? And it's this. And then what we do is we create a new regression model 3, not by running LM or linear model, but by running update and providing to update a linear model that we've already created, and then giving it an option of some kind. And here what we're saying, subset it by removing, this is a minus sign over here, removing these two indexes. We run that, and then we have a new regression model which we can compare to our previous regression model. In any event, that's a whirlwind introduction to linear regression modeling in R.